Good morning, good afternoon, good evening, and good night to anybody who would be watching this video. So I will be talking about conic sections in the course of F&D Math, foundational course in mathematics. So yeah, conic sections in F&D Math. I will be your tutor for today, Jeffrey John Ciabanes, BSMS in Chemical Engineering, and this is my emails if you guys have any further inquiries. So our outline for today's video is, yes, conic sections, and it's four different types: circle, ellipse, parabola, and hyperbola. Their corresponding formulas, and we will be tackling some sample problems. And at the end of all this, I will be giving you a few tips and tricks so that you guys can ace your tests if ever. So conic sections, what are they? So from the name itself, it comes from the cone. So there's like two different cones stacked on top of each other invertedly, and it just depends on how you cut the cone. So the very first that I would like to talk about is the circle here. The circle is when you cut the cone horizontally, there's no angle, just straight up horizontal cut, and it will be a perfect circle. Now, when you introduce a bit of an angle to it, that's when you get an ellipse. An ellipse, it looks like an oval. So, yeah. Once you get to a more, I don't know, once you add more angle to it, and it starts to go off the map, that will be like a parabola. So you see, it's still like an oval, but it's no longer complete. Then the last one, straight up vertical, it is the hyperbola. That's as much I will give you in terms of its shape. So next we'll move on to the general equation of the conic sections, which it is in the ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. So all of the conic sections earlier followed this general equation. And here we would tackle how will you identify what type of conic section it is based on the equation. So we will use what is called a discriminant test, and that is b squared minus 4ac. So if a is equal to c and b is equal to 0, so there's no xy, then it is a circle. If the discriminant test will yield less than 0, then it is an ellipse. If the discriminant test yields 0, then it is a parabola. If the discriminant test is more than 0, then it is a hyperbola. So you can see the sequence here, from circle to ellipse to parabola and hyperbola. So we will now tackle the most simplest of all the conic sections, the circle. So with its general equation of x minus h squared plus y minus k squared is equal to the radius squared, with its center at being hk. So I would like to go on here to Desmos and show you how it works. So with the radius being 1 here, we can change it around. So yeah, with its center at 0 and 0, which is here, h and k. If we move the r, the circle gets bigger. So yeah, now it will be at 2, negative 2, 0, 2, 0 here. So yeah, it would look like the radius is 2. Now, if we want to move where the center it's at, we just change things around. So yeah, now the h is at 1, so the center is at 1, 0. If we change the k, it also moves up and down. Take note that there's a negative sign. So in the equation, it would look like y minus 1, x minus 1. And if it's negative, it would be going to the right. If it's positive, it would be going to the left in the original equation before you translate it to h and k. So yeah, the h and k determines if it goes right, up, left, down, and that is how we would usually look at it. So that is all for circle. We'll move on to the next one. So ellipse, it's a big jump in difficulty immediately. So there are two types of ellipse. There's a horizontal and a vertical ellipse. Now, a horizontal ellipse is one where it stretches horizontally. So like an oval that stretches horizontally. So its general equation is x minus h squared all over a squared plus y minus k squared all over b squared is equal to 1. No longer the radius. It's just straight up equal to 1. It's not dependent. And now its foci, or the plural of focuses, since there will be two focuses now in ellipse, is at the points of h plus minus c, k, close. So the c here is from the equation c squared is equal to a squared minus b squared. Now you might be wondering what are all these new letters. So like we discussed earlier, H and K are used for the focus or the center. So that's still the same here, H and K. Now what is this A and B? A and B here is the major axis and the minor axis of the shape. So directrix is also x equals to h plus minus a squared all over c. And there's the latus rectum length. Latus rectum is like the length that is passing through the foci here that touches the edges of the shape. And then there's eccentricity, which just tells us how much it curves. So here's the equation, E equals to C over A, where E is supposed to be between 0 and 1. So eccentricity, it can also tell you the shape here. If it doesn't fit this 0 to 1, then it is not an ellipse. It is another shape entirely. So let's go now to here, and we have the general formula of ellipse here. I already have it wide. Let's pull up A and B. Who else do we need? We need H and K. So here, our H and K are still 0 and 0, but it is now affected by the C. Yeah, the C that is computed when we have A and B. So like our H and K here will be, let's see, we have 2, 1. I think the focuses will be at square root of 5 and 0. Wait, no. That seems wrong. 2, 1, 2. Ah, wait, no. Square root of 3. It's minus. So here's the that's the focus. 2 squared, yeah. Let's bring this up here. So yeah, as you can see, if we change it to 1, it will start to look like a circle. So these denominators are the ones that give it its unique shape of being an oval. It still follows that if you move it to the right or left, up or down, the H and K. But these A and B, if it's 1 and 1, that is just it's just a regular circle, you know? It doesn't change at all. But if it starts to change the values here, wait, I want to try something. 5 and 4. That should give us an even 3 here. So yeah, this is the focus now. There's another focus, which is when C is negative, so that will be negative 3 and 0 here. So yeah, these are our focus for the ellipse. We can invert it. If B is bigger now than A, it will start to turn to be a vertical ellipse. So our focus will also shift. The C will be adding into the Y value instead of the X value. These are our focus now. So the latus rectum, which I don't know how to make the equation, but the length of it, it will be stretching from here, let me get the 3. So this negative 3.2 to this 3.2 also here at the 3 value. Can I do that? I have no clue how to do that. But the latus rectum length will be 6.4 because, let's go back to the equation of the latus rectum length. 2b squared, so 2, 5 squared, oh shit, divided by 4, 12.5. Oh wait, no, this is inverted. So always the b will be the shorter one. Yes, the b will be the shorter one and the a will be the bigger one. So you have to take note of that. So 6.4, right? Because it hits the 3.2 here and to the negative 3.2 here. So 3.2 plus 3.2, the entire length is 6.4. It just makes us touch the edges of the shape. That is the latus rectum exactly. And yeah, the eccentricity is how fat it is, you know? That's just, yeah, so like if it gets thinner, if it gets more gaunt, that's basically how I would describe eccentricity here. Now, I feel like I've covered enough of how much the ellipse works. Let's move on to the next one. It's the parabola this time. So, parabola, it is only showing up or down or left and right, and it extends, no, infinitely. It's the U shape of the conic sections. So the general equation is x minus h squared plus is equal to plus minus 4a y minus k, and the foci is at h plus minus a and oh wait k and yeah, where was I? The foci h plus minus a and k. So there's no other calculations here. It's just very simple. There's only an additional a. Oh, I forgot to change here my x and y for the left and right. So we'll be taking note of that in the decimals here, which I have changed. Yeah, let's close these, and we'll be seeing who do we need. We need h. Let's put down this h, k, and 0. So yeah, the h and k, it's this. It just moves the center again. So h and k always they move the center around. We add more h, it goes to the right. We add more k, it goes up. All right, always. So now for the a. So the a determines how wide it gets again here, because it determines the latus rectum length as well. Now, what's the latus rectum? It's the from the focus, how much it needs to go through to touch to the other side here. So our focus is at hk plus minus a. So if our h and k is 0 and our a is 1, then that is when our focus shifts. Oh, here's the parabola. So yeah, y minus k, x minus h. And it just shifts around like this. This is also related to the quadratic equation of x squared minus, no, ax squared minus bx plus c is equal to 0. It's often linked to that because, yeah, as we can see, there's also the discriminant, which is also in the original quadratic equation. So yeah, just take note y minus h and h minus k. Then we move on to the hyperbola. It is almost close to the ellipse, But there's a significant difference. Instead of plus, it is now minus. And here in the C, instead of minus, it is now plus. So it's just changing the signs here. We're just changing some of the signs. And now there's an asymptote. So an asymptote is, since the hyperbola is like two parabolas that are facing away from each other, they don't like each other. There's a slope of line that goes through it, and it's really fun to look at, you know, because they don't they it will never touch that line, basically that asymptote, but it is so close to that line. So yeah, here there's a horizontal and vertical. So like horizontal is when they look left and right away from each other, and vertical is looking up and down away from each other. And of course, there's still the focuses, which is plus minus C. On If it's horizontal, then it's on the X value, and if it's on the vertical, it's on the Y value. So here we'll be looking at all these. Latus rectum length is the same. Eccentricity is the same formula. We just have to take note that it should be more than one this time. Because that's how it works. So yeah, we should dive in here. What do we need for this? Oh, should I have? No. It depends on the values that we have. Let's bring this up. So HK and B. B is making it super wide. So as you can see, it moves left and right again from the K, H and K, up and down. A is making it further away from each other. B is making it wider and wider. Alright? So there's a distinct difference on who gets who. So if we were to invert this, let's see, like put this in front of the other, minus this is equal to 1. Now that would be the vertical version of it. As you can see, they're so near each other. If you can see, if you just invert it, since they're the same values, those are the asymptotes that they're looking for. It is so close. The lines that they will never meet, that closely similar is to the asymptote that we're looking for here. They'll never hit the line. So our focus here is around C. So wait, let me just do, let's have A equals 3, B equals 4. Make it a bit bigger, you know. So our C is equal to 5 based on the 3, 4, 5 Pythagorean. Let's have 5, 0. It's automatic. Let's have negative 5, 0. So it's, as you can see, the focuses are no longer within the shape. It's outside now. It's like the parabola version, right? It's on the U. So our latus rectum would be going from this 5.33 to this negative 5.33. So that's like 10.6667. Oh my god, 67. So yeah, so 0, 5 for the vertical one. It's over here. And 0, negative 5. As you can see, their latus rectum is different because our computation is the smaller axis all over the major axis, the minor axis all over the major axis. And the minor axis here will be smaller. So yeah, gets better and better, right? It will be like 2.2, so like around 4.4, I think. Wait, no, it's around 2.5, 2.6. I can't tell. My eyes are not that good. So yeah, eccentricity almost the same here. You just have to take note the changes of signs from the ellipse. They're similar to the ellipse. The asymptote you have to take note of how to get the slope of this, which if you're just gonna look at the slope, it's b over a here or a over b here. Those are the slopes of the asymptotes. That is mostly what the professors would like to ask you in the questions, the slope of the asymptote. So you have to take note, does my hyperbola look right and left? If it's right and left, then it's the minor axis all over the major axis. If it looks up and down, uh, then it's the major axis all over the minor axis. Those are the only things that you have to take note of, you know? And I think that's all for all of them. So we could start with our first sample problem, which I feel like most of the professors would like to relate to it. It's the orbits. They like to compare the orbits to an ellipse because there's no orbit that is a perfect circle. So here, I took the example of the Halley's Comet, which arrives every 76 years and showers us with its beauty, you know? Oh, I misspelled that. Showers you with its beauty. So, if this comet's nearest point to Earth will be 7,000 kilometers and its farthest point be 21,000 kilometers, let us find its eccentricity, length of latus rectum, its focal distance, semi-major and semi-minor axes, which are A and B respectively. So, let's tackle into solution. So we're given from a point the nearest and farthest one. So what does this tell us? From a point, the nearest, let's start drawing it. Let's have paint though, you know. So we have this, we have a point. Let's say that's Earth. The nearest point in an ellipse will be here, right? And the farthest point is all the way over there. So it's saying this is 7,000 kilometers. Yeah, 7k km, you know. That's not the correct term, but like 7k km, you know, like that. Because I'm too lazy to write the entire thing. Right. Then we have 21k km. I feel like this is a megameter supposedly. Is that right? Yes, megameter. Pero I'm gonna write it like 21,000 kilometers. So this entire thing is 21,000, and that's 7,000 kilometers. So what does that tell us? So we know that this entire thing is 2a. This is 2b. Like in the center, that's 2b. So like this is the major axis. When I say A is the semi-major axis, I'm only talking about half of it. So like that's the A. But if it's the entire thing, it's 2A. Just a better representation of it. So B is the semi-minor axis, which is the shorter one here. That's when you have it, that's the B, semi-minor. But 2B is the minor axis. So like the entire shorter, the maximum of that vertical or horizontal one. So yeah, so how I would compute for it is first I'm gonna solve for A. So the A here, I'm gonna add 7,000 and 21,000, then divide it by 2, because the entire length of this is equal to 2A. Alright, so that would give me a 14,000 kilometers for A. Now eccentricity, how did I get it as like far minus near and far plus near? Because it just determines how fat it is. So if I were to like go like that and go like that, I just need to get the length, that is how much length it took from here to here and how much is the entire thing. That's how I look at it, and that would give me 1/2, which is which still follows one of our rules of eccentricity here, which says that eccentricity should be between 0 and 1. So now we'll be moving on. Now that we got A and E, we'll be using our formula of E is equal to C over A to get our C. So we're gonna be multiplying the value of A that we got here and the value of E, which is 14,000 times 1/2 is equal to 7,000. So that is the value of our C here. So our C, we can use our C to get the points of our foci if ever, but it is not asked in this question. So we'll just be using C to compute for B. We're gonna be looking for B through the formula of C squared is equal to A squared minus B squared. So let's isolate B here. If we're gonna isolate B, we're gonna move it to the other side, the negative turns to positive, and this C squared will have to go here. So it's gonna be A squared minus C squared. And then since it's still B squared, we're gonna have to square root the entire thing, which is what happens here. So we have our value of A here, 14,000, and our value of C, 14,000 squared minus 7,000 squared, and we're gonna square root that. So how did it become to 3 times 7,000 squared? So what I did, you see this 14,000, right? If you split it, I love splitting it. So 14,000, right, is equal to 2 times 7,000. But that's still squared. So I'm gonna take this out. It's gonna take a square with it. So 2 squared is 4 and times 7,000 squared minus 7,000 squared. So like I can just think of it like it's 7,000 squared is 7,000 squared. It's the same thing. It's like 4. If I would replace the with x, it's gonna be like 4x minus x. So it's just gonna be like 3x, and that's what happened here. 3 times 7,000 squared, where x is 7,000 squared. That's how I would like think of it. I treat it as a variable. I won't care for it. I won't solve for it. Then like take it out later. So like here, I see that this is a square in a square root, and it's just multiplication now. So I'm gonna just take it out. I don't want to compute it. I'm gonna just take it out, remove the square, leave square root of 3 inside, the lonely square root of 3. So that will be my value for B now. I got the value. 7,000 square times square root of 3. That's my value of B. That's the semi-minor axis. Now, the length of the latus rectum, the last one, we're just gonna follow the standard formula. 2B squared all over A is equal to, so we'll substitute our values in. 2 times 7,000 times square root of 3 squared all over 14,000 is equal to 21,000 immediately. But I'll show you how I would solve it, like here. So this has a square all over 14,000. I see again, this is just 7,000. This is 7,000 squared. Take that out, take this out. So it's just 7,000 times square root of 3 squared. Now I see this, the square and square root, they just cancel each other out. So it's 7,000 times 3. Just some tips and I like to isolate, I like to distribute it. I wanna see how it all works out, and that's how I would compute it very very fast. So like there, we got all of the required here. E, A, B, C, E, L, and blah. So that's it for our first sample problem. The teachers, they would very much like to do these orbits, like satellite. It doesn't have to be a comet, satellite, whatever. Our planet, maybe. Is there some? Yeah. So like satellites, comets. I don't know what kind of term they'd use, but this was one of the examples given before. So on to our second sample problem. It is a satellite dish that is 12 meters wide and 3 meters deep. So first, let's see. It usually won't state that it's a parabola, but I just wanted to state the parabola immediately. But you imagine, what's a satellite dish? What's the shape of it? It's a U shape, isn't it? Yeah. So with that, the satellite dish, that's 12 meters wide and 3 meters deep. Let's have a new drawing. You know, I always like to draw. You know, like draw. So yeah, everything would be bouncing up to uh, to a singular point, which is the focus of it. Not the center, it's the focus. So here, yeah, we're gonna be looking for the equation of how it became this U shape or whatever, and try to look for the focus and the length of the latus rectum. So like if the satellite were to continuously go up, what's the length before it touches the sides, right? So 2 points are given, and that is y equals to 3 and x equals to plus minus 6. Because if we're gonna look at it, this entire thing is 12, this is 3. So from the middle here, we're gonna split it in half, right? So 6 and 6. It's just gonna be the point here, the value of this point, it'll be negative 6 and 3 from the center. Then this point, 6 and 3. So, oh, a satellite always points upward. Wait, no. What am I talking about? No, this what do you call it? It's a satellite. It is a satellite. It's a satellite dish. Always points upward. So I'm using the up down general equation, which is usually x minus h squared is equal to 4a y minus k. Now, why is there no h and k? Because we're not looking for a specific point. We're just looking for a random point anywhere, you know. That is why I chose to they did not give a specific coordinates that we would have to use. So it will be fine if if I don't follow the strict format of the h and k. Basically, there's no h and k given, so I would not think about it for now. So the general equation, which will, without the h and k, will just be x squared is equal to 4ay. Now we have our value of x, which if squared, it's just gonna yield the same 36. And then we have our value of y, which is 3. So 3 times 4, that's 12a. And now we have our a. Now if we got our a, we can look for everything else. Our general equation now will be x squared is equal to 12y, right? So now our latus rectum is equal to just 4a. So that it's just our a here is 3, so 4 times 3 is equal to 12, and our focus point is at 0, 3. That is it. So yeah, that's it. Maybe it's good if I would show you here. Let's take this all out. We're on this. H and K is 0. Wait, no, this is not the one. Where is it? This one. No, this one. Yeah. Our focus will be at 0, 3. And we can get our points, right? Negative 6, 3. And 6, 3. Which I feel like this is also the latus rectum, right? It would go straight through all these points, and that will yield a 12 length. That is our length of latus rectum. So this basically was our latus rectum. Sometimes it goes above, the focus goes above, and that will have to go through a longer latus rectum. But apparently in this question, the focus is already here. So we don't have to do that. So yeah, this is another example that I feel like the professors would very much like to use, the satellite dish. So yeah, and I think that is it. Yeah. So summary, I usually try to look for the what type it is using the discriminant, of course, b squared minus 4ac. If a and c is the same and b is 0, then it's a circle. If it's less than 0, it's an ellipse. If it's equal to 0, which is a famous one, in the quadratic equation again, since it's a parabola. Quadratic equations yield a parabola. So yeah. And just remember the formulas because on my test I forgot about the formulas and I was trying to derive from the drawing, but I had to draw it. You should practice like imagining the shape, imagining the equation, translating the equation into an image of the object. Yeah. You should practice that because that's where I was like, what does this look like? And that was my struggles with FND math. So